In this video, we're going to discuss interpretations of the definite integral. Remember, when we were discussing the definite integral previously, we used this integral, right? For instance, we defined the integral from a to b of f of x dx as the limit of a Riemann sum. The specific limit is the limit as n approaches infinity of either our left hand sum starts at 0 and goes into n minus 1, of f of x sub I times delta x, if we have an f of x here. Remember, there are some similarities between these two expressions here. This sigma notation is very similar to this this s for our integral symbol here. It looks like an elongated s. Our f of x, which is the function that we're taking the integral of, our integrand, is like our f of x sub I here, and our dx here is very similar to this delta x here. By knowing this relationship, and we know that we can use our left and right hand sums, this is the notation to do the areas of the rectangles, this can help us come up with the units of our integral. And once we know the units of our integral, we can come up with our interpretations of the integral. And so it says, determine the units of the integral from a to b of f of x dx. We can use the units of the Riemann sum. Well, the Riemann sum incorporates a multiplication of our function f of x and our delta x. Now remember, delta x is b minus a over n. That is what delta x is. And remember, this a and b, those are our intervals, our subintervals. I'm using t because when we first started doing this, I used the variable t as our input variable, but now we have x as our input variable. X as our input variable, and x runs from a to b. And so when I do this b minus a, this is in the units of x, and this is just dividing that interval into sub-intervals. And so we divide that by n, which doesn't have a unit, so that's still going to be the units of x. So this delta x is the units of x, and then we're multiplying that by this f of x of I. And so our units of our integral is going to be the units of f of x times our units of x, which is the same thing as that delta x, all right? And so we have some examples where we want to find the units. We have the integral, the definite integral from a to b of v of t dt, where v is measured in miles per hour and t is measured in hours, right? Well, this is going to be the units of v times the units of t. Now, v is a function of t, so if you wanted to write v of t, that's fine. Well, the units of v is miles per hour. I'm going to write it out here. And then units of t is your hours. Notice that your hours cancel, and so you're just left with miles. So this integral from a to b of v of t dt is going to be in miles. In part b, we have the integral from a to b of c prime of t dt, where marginal cost, which is that c prime, is measured in dollars per year, and t is measured in years. And so my units of my integral is going to be the units of c prime of t, which is dollars divided by year, and then I multiply that by the units of t, which is in years. And notice here my years cancel, and I'm just going to be left with looks like an integral symbol. It's just going to be dollars, or I'm going to use my dollar sign there. All right, so the units of this integral is dollars. The units of this previous integral is miles. And so this gives us the units, and now we just have to incorporate what we've known about the integral, right? In both of these cases, notice here, this c of c, this is not c of t, it's c prime of t. It's a rate. This is a rate of change. And in this example, this is a rate of change. It's a velocity. It represents miles per hour. That is a rate of change. And so when we do the integral of a rate of change, what we're doing is we're taking the rate of change, multiplying it by the variable in which it's changing by. And when you multiply the rate of change in an output by your change in your input, you're going to get the total change or the accumulated change. And so as we've said before, when you integrate f prime of t, which is the f which is the rate of change of f of t, from t equals a to t equals b, you find the total change in f of t in your regular function, not your derivative, but in your regular function between t equals a and t equals b. Some other words besides total, you may hear people say net change, and you may also see people write accumulated change. All of these are basically identical statements. And so what we're going to do is we're going to use this in order to help us make interpretations of the integral. And so it says, explain the words what the integral represents and give units. Here we have the integral from 2000 to 2004 of f of t dt, where f of t is the world population growth in billions of people per year, and t is time. What I'm going to do first is I'm going to write the units, right? So the units of this integral is going to be, all right, well, to find that, I'm going to have billions of people per year, because that's my units of f of t, so divided by year, and I'm going to multiply that by my units of t, which is years, right? Well, notice the years cancel, and which means my units is going to be billions of people. All right. So the units of this integral is billions of people, right? But to interpret the integral, we have to incorporate not only the fact that this is going to equal the billions of people, but it's going to be the total change, or I could use the word the net change or accumulated change, specifically between t equals a and t equals b, right? So this integral represents the total change in the world population in billions of people from the year 2000 to the year 2004, right? Now, we know that this is a population growth, right? And so this represents, if you didn't want to say total change, which is perfectly fine, you could say this represents the growth in the world population in billions of people from the year 2000 to the year 2004, or from 2000 to 2004, right? Either of these work. I don't know why I strike through total change, but you could also use growth instead of total change here. Total change is not incorrect. So I shouldn't have strike that through. And so I'll just say that you could have said growth instead of total change. All right. And we know it's growth for the simple fact that this said that this represented the population growth. All right. And so that's why I say, oh, that might give a better interpretation. All right, let's look at another example. It says a holding tank initially contains 1,000 liters of water. Water is pumped out at a rate of 5 minus 5e to the negative 0.12 t liters per minute, where t is the number of minutes since the pump started. Part A, give the definite integral that represents the total change in the amount of water that was pumped out 1 hour later. Now, we just reviewed the fact that the total change in the quantity can always be found by doing the integral of the derivative of whatever function you have the rate of change, if you want the total change in, right? So the total change in f of t is going to be found by doing the integral of f prime of t, the rate of change of f of t. And so if I want to know the total change in the amount of water being pumped out, I need to know the rate at which the water is being pumped out. If I know the rate at which the water is being pumped out, I can do the integral of the function that represents that rate, and I can get the total change. Well, in the beginning of the problem, they tell us the function that represents the rate at which water is being pumped out. says water is being pumped out at a rate of, and I have this function here. It is a function of t. So I know for me to get the total change, I'm going to go do the integral, and I'm going to write my function. Now, I'm not going to say like f of t. I'm going to actually put the formula in for the function like we've seen before, right? And I just have to make sure that I have my limits of integration. Now, notice this is a function of t. Um, our derivative is a function of t, and it's given in liters per minute, and t is in minutes, all right? So when I write my limits of integration, it has to be in minutes. Now, I want to know how much water is being pumped out 1 hour later, right? So the pump initially holds something, and then I want to know how much is left. I want to know how much is being pumped out 1 hour later. So I'm going to start at 0 since that represents the initial, and 1 hour later is actually 60 minutes. And so I have to know to change that 1 hour to 60 minutes, and that's going to give me my limits of integration. So this integral right here represents how much water is being pumped out, the total change in the amount of more water that's being pumped out. All right. Part B says how much water is in the tank after 1 hour. Now, for us to figure this out, all we have to do is figure out that integral. Well, this integral tells us how much is being pumped out. We know we're starting with 1,000. So if I start with 1,000, I need to subtract from that the amount that has been pumped out after 1 hour. And just for fun, once again, we can put this in our calculator, and it's going to tell us what our answer is going to be. And so let's get our calculator, and we'll do this integral here. I'm going to do 1,000. Now notice if you don't have a calculator, that's a graphing calculator, you won't be able to do this. You'll have to use a left and right hand sum, choose an n, and you'll come up with your estimate. But since we have a calculator as recommended, I have 1,000 minus. To do an integral without doing a graph, we go to math. And if you scroll down, keep scrolling down until you get to option 9, you're going to have your integral. I'm going to put 0 for my lower limit of integration, 60 for my upper limit of integration. I'm going to have a 5 minus 5e, and that's raised to the negative 0.12. Okay, I don't have a t here, so I'm going to put an x. I close that parenthesis, and I'm going to put an x here. Now, I put an x here because I'm using my x variable in my calculator, which is kind of automatic here. And if I put an x here, I have to put the dx there, right? That variable has to be the same. I'm going to press enter, and I'm going to see I get 741.64 liters are left. 741.64. Sorry. And remember, my units are going to be liters, or not, again, to get the units, liters per minute times t, which is in minutes. Notice the minutes cancel, and we know that we have liters as our units. So there should be 741.64 liters left. And that is how we can use our integral, our definite integral, to help us find out the total change or the accumulated change or the net change in our function when we're given the rate of change of that function over a specified interval. One more example, it says the graph below shows the rate of growth of 2 trees. If the 2 trees are the same height at time t equals 0, which tree is taller after 5 years, and then which tree is taller after 10 years? Notice here, my horizontal axis has years, right? My vertical axis has the rate, which is in feet per year. So it's the rate of change of the height, and the unit of change is years, right? I'm going to call this function a of t, this rate of change of tree A, and I'm going to call the function that represents the rate of change of tree B, b of t. Now with that, now this is before we even start to answer this question, I want to show you conceptually what's happening here. If I want to know which tree is taller over a certain time period, I'm going to look at which integral is bigger, right? Because the integral represents the rate, the total change or the net change in your quantity, right? So if I did the integral from 0 to 5 of a of t dt, right? And a of t is the rate of change, which is this graph right here for tree A, right? This equals the total change in the height of tree A over the first 5 years, right? And then if I did the integral from 0 to 5 of b of t dt, this is going to give me the total change in the height of tree B over the first 5 years, right? And take because those represents rate of changes, right? Now, with that, I have a graph of a function. And if I want to know something about that integral, remember we said that the integral represents the area between the x-axis and that curve. And so if I want to know which tree is taller after 5 years, and this integral gives us the total growth in those trees, all I have to do is to evaluate this integral by looking at the graph and seeing which one has the more area under the curve, right? And so if I look at the first 5 years, for instance, I'm going to use, all right, tree A, I'm going to use the color blue, and tree B, I'm going to use the color red, right? If I want to know which is taller, I have to see which one has the larger area under its curve for the first 5 years. So if year 0 is here, year 5 is here. Under tree A, this is the area under the curve for tree A, and the area under the curve for tree B, which represents this integral here, which is the total change in height. For tree B, is this square root function looking curve. It's this entire area here, right? Which area is larger? The area for tree B, right? So I could say after 5 years, tree B is taller. And one of the reasons is because the integral from 0 to 5 of b of t dt is greater than the integral from 0 to 5 of a of t dt. That meant the total change, the growth in the height of tree B over the first 5 years was greater than the total change or growth or height in growth in height of tree A over the first 5 years. All right. And then after 10 years, we can do a similar calculation, but now we're doing the total area under the curve for tree A and B, which goes from 0 to 10 instead of 0 to 5. And so if I continue this process here, we can see that for tree A, all right, tree A will have all of this area here, including this initial area, and tree B, its height will be just this area under this curve. And of course, we can see that tree A has a lot more area. They share this common area here. So the common area that they share, now I've messed up my picture, but they share this from 0 to 10, they kind of share this common area. This is tree B having more area, and this is tree A having more area. And of course, this blue area is bigger than this red area that I shaded in. So after 10 years, tree A is taller. And that's because the integral from 0 to 10 of A of t is greater than the integral from 0 to 10 of B of t dt. Both of those are dt. And remember, this represents the total change in height over the first 10 years, which represents the area under the curve A for the first 10 years. And that area is definitely greater than that of tree B. All right. So when you're using the graph, you can evaluate an integral by finding the area under the curve. Since we didn't need to know the exact height of the tree, then we can just compare the amount of area between the x-axis and those curves to help us answer that question. All right. This concludes this video. We'll see you during our next one.